I'm going to run through a few undergraduate, high school level chemistry questions. So for the first one, we have a unit conversion question. So it just wants 459 gallons per minute turned to feet cubed per second. For this, I'm just going to use a gallon to feet cubed conversion. So 1 gallon is 0.133681 feet cubed. So that means that 459 gallons per minute can be converted to feet cubed per minute by multiplying by this factor. Okay, and we always do it such that the units cancel, and then we get 1.02266 feet cubed per minute. And then to get it to seconds, we multiply by our second conversion, which is 1 minute over 60 seconds. Again, do it so that the units cancel. And then we get, oh, I jumped a step there, sorry. So that's not that. That's actually 61.359579. There we go, that makes more sense. Divided by 60 is then 1.02 feet cubed per second, where I've dropped the number of decimal places I'm keeping in my final answer to match with the significant digits, and so then that's our final answer. If we check the solution here, so we just multiply by the relevant conversions, and that looks good. Okay. Okay, so now for this one, it's asked to specify both the electron group geometry and the molecular geometry for a set of molecules. So you can't see all four there, but I'll preface each one by saying what they are. So the first one is CH4. This is my second question. For CH4, we have C. We can start off by drawing our Lewis structure. And I just do this by simply putting in all the valence electrons and seeing if we get nice bonding, which we do. And so this looks like the right structure. Of course, when we draw it into the molecular structure, it's going to be three-dimensional. Okay, so these filled in wedges I'm using to show that it's coming out of the page. The dash I'm using to show that it's into the page. And so our electron geometry is tetrahedral, and our molecular geometry is also tetrahedral, right? So there's of course a table for these, but some of them you just start to remember because you'll see them a lot. So the electron geometry is AX4. meaning we have one central atom and four connected atoms, and so that's tetrahedral. And our molecular geometry is also AX4 or tetrahedral. Okay. The second one. Okay. The second one is pH4 plus. So again, I'm going to start off with my simple Lewis structure. I can be pretty sure, since it's got the same structure, that it's going to be the same. So it's pH4 plus, so we're missing an electron somewhere. So phosphorus normally has 5. So right now it has 4. And that does give us nice bonding with octet rule satisfied. And there's only 4 electrons there. It normally wants 5. So that's a positive charge. So our positive charge is sitting on the phosphorus, and we have 4 bonded hydrogens. So making this into our 3D structure. Be something like this. So our electron geometry is again AX4 or tetrahedral, and our molecular is AX4 or tetrahedral. Okay. Okay, so then the next one is pH3. So pH3. Phosphorus has 5 valence electrons normally. Without the positive charge. So there we go. And that bonds up nicely, so it looks good. And so we have this. And so our 3D structure is going to be something like this. Where now our electron geometry is still AX4 because we count our lone pairs in our electron geometry. So that's tetrahedral. But our molecular geometry is, so you might see different notations for this, but I'm going to use just a B for our lone pairs, so B AX3. So that means we're only considering for molecular geometry, we're only considering the atoms, not the electrons. And so this is a trigonal pyramidal structure. Okay, so here's one case where they differ. And then the last one is NO3. And again, so there's 5 valence here and 6 valence on each of the oxygens. NO3 minus. And so there's 6 times 3 is 18, plus 5 is 23, plus 1 is 24, so 24 valence in total. So if we try to do our simple Lewis structure. Then, of course, we get something like this. The extra electron we can just add in somewhere to fill up an octet, so that guy's happy. He has 7 electrons around him, 5 electrons, 6 electrons, and 6. So these are neutral. This guy's got a -1 charge. The nitrogen's octet is filled, but these two, the octet is not filled. So we need to fill that up. So the best way is to convert one of these electrons into a bond and donate that guy over there. Or not donate, I guess that's a bad word for this, but move that electron over there. And so we get a double bond here, and then this guy would be, and then everyone would be full octet. So it'd be something more like this. And if we check our charges, so there's 7 electrons here. There's 4 electrons here, 7 here, 6 here. So oxygen normally wants 6, so this is a -1 charge. Nitrogen normally wants 5, so it's a +1 charge. And oxygen normally wants 7, so that's a -1. So -1 + 1 is 0, -1 is -1. So the whole thing's -1. If we count the electrons, 7, 14, 20, 24, so we're good. We got the right number of electrons, and all the octets are satisfied, and so that looks good too. So that's our appropriate structure. If we draw the 3D structure now, all the electrons are going to be try to be as far away as possible, but the double bond is going to constrain it, so it's going to be something more like this. Okay, so our electron geometry is AX3 because there's only 3 bonded partners. And so that's a trigonal planar. And our molecular geometry is also AX3, so trigonal planar. Okay, so those are the 4 molecules the question has to solve. So here's the table. Here's a table like I had mentioned. And so these tables can be found in lots of places, and in your courses you're probably also given one. As I said, you end up memorizing a little bit of the easy ones, but of course the higher ones might take some doing. So draw our structures, figure out how many are around it. And so for CH4 it's tetrahedral. For pH4+, we again have 4, so it's tetrahedral. For pH3, we have a single non-bonding set of electrons and 3 other ones. So the electron's tetrahedral, but the electron's tetrahedral, but the molecular is trigonal pyramidal. For NO3-, we have only 3 constituents, and so it's trigonal planar for both electron and molecular. So that looks good. Let's see if that's correct. Okay. order for me. Okay. So why do we believe that the valence electrons of calcium and potassium reside in the 4s orbital rather than in the 3d orbital? So just as a reminder here, so for H, our energy levels are given by minus R over n squared. And so n here is our principal quantum number. And it ranges from 1 up. So those are the values that n takes. They're all integer and non-zero. L is our orbital quantum number, or azimuthal, and it equals 0 up to n minus 1. So for a given n, your L can only go up to n minus 1. And these labels are these numbers are what we usually use for our SPD labels. So L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. Now, if we look at this equation, we see that for an H atom, energy only depends on 1 over n, or 1 over n squared, I should say. So L doesn't come into play, right? So that means that a 3s, a 3p, and a 3d orbital all have the same energy, right? A 4s, 4p, 4d, same energy. And so in a hydrogen atom, it doesn't matter what the L is, it only matters what the N is. Now for multi-electron atoms like calcium or potassium, L does start to matter, and so our energies do shift, but N is still, this equation still roughly holds, so our energies are going to increase with 1 over the principal number in multi-electron atoms, but L is now going to have an effect as electron repulsion starts to become a factor as we start to fill up these larger and larger atoms. Now how we can account for these easily or remember them is given by Madelung's rule, which states that orbitals are filled up by n plus L. And for states with the same n plus L, then we go by n. So so that means we fill a 4s orbital, which is n equals 4, L equals 0, before we fill a 3d, which is n equals 3, L equals 2, right? So 3 plus 2 equals 5. 4 plus 0 equals 4. So 4s comes before 3d, and of course this comes before A4p, which is n equals 4, L equals 1. So 4 plus 1 equals 5, but the n is lower. And this is just to take into account the fact that electron repulsion is now becoming a thing, and sometimes it's better to fill up these higher L orbitals before we fill up lower L orbitals, as long as we're not paying too high an energy cost, which would be represented by the N value. Okay, so Magdellan's rule, we fill by N plus L first, so 4S is 4, 3D is 5. Okay, so that looks good. Okay. Okay. What is the Lewis structure for BF3? Okay, so BF3. So boron has 3 valence electrons. Fluorine has 7 valence electrons. So we can start off by trying to do our simple, just put the number of valence and align them around. And then attach. I got so many dots now. And we see that we have 7 here, 7 here, 7 here, 3 here, so everyone's neutral. We have a full octet around fluorine, or each of the fluorines, but we don't have a full octet around boron. But there's no way to get a full octet around boron, not without sacrificing charge separation, or having weird bonding structures around the other atoms. I guess we could donate one of these lone pairs in, but that would make fluorine positively charged, which it doesn't like doing. And so in the end, this molecule just prefers to be like this, and boron is essentially one of the main atoms that breaks our octet rule, or main exceptions to our octet rule. So there's only 6 electrons around boron, and it's fine. Yeah. So if we check here, so there's our electron count, and boron is an exception to the octet rule. So this looks good. Okay. What is the electron configuration of chromium 3+? For this, I'm just going to grab a periodic table and do a bit of shrink and migration. Okay. So chromium sits here. And so we can figure out our electron configuration by running around the table. Remember that helium is really here. And so we can just go right across. Remember that that's the S block, this is the P block, and this is the D block. And down here is the F block, and the F block inserts here. Okay, so we can run across the table. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Okay, so once we've done this, we need to check, because this is a case where we get half-filled orbital stabilization, and it really only comes into play with the D block because of how many it has. It might come into play with the P sometimes, but it's much more common in the D block. So in this case, we can get a half-filled orbital by moving one of these electrons, and so we will. And so that is, so this is the electron configuration for our chromium. Now for chromium 3+, as we remove electrons, we still remove electrons from our highest n orbitals first. Remove from our highest n first. So that means this guy goes first. So 1. And then we need 2 more gons. So this 5 is going to turn into a 3. So then we've got 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. And so then that is our electron configuration for chromium 3+. Okay, so checking the solution here. So they've correctly noted that we get our half-filled orbital stabilization for D. But we don't pull the 3 electrons from just the d orbital, we take from our highest n first. So so I'm just gonna label this with our, what is the argon, so should be argon 3d3 and wink. Alright, so that one was incorrect, but that's okay. Alright, so here we have a rate solving question. We can't see the question here, but I'll draw out the table. So we have this equation, just a general chemical equation, and we're given 3 trials and initial concentrations for each of the 2 reactants and a measured rate. So for trial 1, 0.250, 0.200, okay, and so now we have 3 trials with 3 different sets of conditions and 3 rates. Our general rate law is going to be our rate constant times our concentration of A to some factor, which is the order in A, and our concentration of B to some factor, which is the order in B. And the question wants us to solve for N, M, and K. Okay, so the way to go about this is to write out what our equations are here. So from the first trial, we have at 0.0215, and I should put that the units on this are molars per second, but in solving it just for clarity, I'm going to drop the units. So K times 0.250 to the N, 0.200 to the M. Our second equation is 0.145, 0.250 to the N, 0.520 to the M. And our third equation is 0.0301 is 50 to the N, 0.200 to the M. Okay, so to go about starting this, we basically need to find two equations that we can divide by one another to get rid of the most things so we can solve it. So if we look at 1, we have K times 0.250 to the N. If we look at 2, we have K times 0.250 to the N. And so if we divide these two, those factors will cancel. So 2 divided by 1 is 0.145 over 0.0215 equals K. I'm just going to write them out completely so you can see. And so we can see that the K's will cancel, the 0.250's, the N will cancel, and all we're left with is the M powers. If we run this on our calculator here, so this division here comes out to be 6.744186, and this division here comes out to be 2.6 to the power of M. There we go. 2.6 to the power of M. To solve for M now, we need to take the logarithm of both sides and use one of the log rules. So log 6.744186 is equal to, so if we take the log of this, we can bring the power down. So that becomes M log 2.6, or M equals log of 6.744186 over the log of 2.6. Doing that division using your calculator, this comes out to be 1.998, which is approximately 2. So for the orders, I would say we would always want to round to the nearest integer value. And so it looks like we're second order in B. Okay, so we're second order in B. Okay, so now for our next equation, or to solve for N, we would play the same game. So we would look for two of these equations where we can remove everything except the n's. And so if we look at our 1 and our 3, we have this factor in both of them, And so it looks like if we take 3 and divide by 1, then we will get our n on its own. And so just doing that now. So 3 divided by 1 is 0.0301 over 215, which is equal to, I guess I should write them out completely. So K 0.350 to the n 0.200 to the m. Now we know what m is, but I'm just going to leave it because it's going to cancel. 250 and 200. Okay, so the k's will cancel, these guys will cancel. Running this through on our calculator, we get 1.4 is equal to, and that same division as well, 1.4 to the n, taking the logarithm of both sides. And solving for n. And we don't actually need our calculator here because log of 1.4 over log of 1.4 is just 1. So now now we have both n and m. It's first order in n. So our rate law is k concentration of A to the 1, concentration of B to the 2. Now to solve for our K, we can just use any of our rates. And to get proper units on the K, I'm going to, any of our equations, and to get proper units, I'm just going to put our units back in. So I'm just going to use the first equation. So 0.0215, and that was in molars per second, is K, and A is 0.250 molar, and B was 0.200 for the first trial, and that would be squared. Rearranging for our K, it's 0.0215 molar per second over 0.250 molar, 0.200 molar squared. And so one of these molars will cancel that, but then we're going to have a 1 over molar squared second. So doing this division, not forgetting the square there, we get 2.15, 1 over molar squared seconds. And so there's our K. And so now we've got our full rate expression. So the rate is 2.15, 1 over molar squared second, concentration of A, concentration of B squared. And that's our flow rate expression. Okay, so checking the solution, we use our general expression here. And so we write our 3 equations, divide based on getting the same things. Go to the end, we get Ka B squared, solving for K, 2.15, and it's 1 over molar squared seconds, so that all looks good. Okay. And Okay, so write the valence shell configuration for these elements. I'm just gonna go back here to my table slide and wipe this all down. Just so we can find everything. So rubidium is here. Okay, and so to get our valence shell electron configuration, remember that helium should be here. So that's what rubidium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then 5s1. And so then there's our electron configuration for rubidium. Barium is down here. So our barium is going to be the same as rubidium. So 1s2, 2s2 for at least the initial bits. S2, 3d10, 4p6, and then we've got 5s2 all the way across, 4d10, 5p6, and then 6s2. Okay, and then the next element it asks for is titanium. So titanium is here. So that guy is only, rearrange this a bit so we can see what I'm doing. So it only goes up to this far, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d2. Okay, and then germanium, which is over here. So then it's like titanium, but with 3d10 and then 4p2. So then germanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. And checking your solution against theirs. Everything looks pretty good. So let's say the solution is correct. Okay, fluorine reacts with water to form gaseous hydrogen fluoride and oxygen. The first part is to write a balanced equation. So here we've got fluorine, fluorine gas plus liquid water, giving us HF HF gas plus O2. I'm just going to migrate this a bit. Try to migrate it without it fighting with me too much. And leave some space for balancing. Okay. So to balance this now, so we've got 1 hydrogen on this side and 2 on this side, so I'm going to plunk a 2 there. But we need 2 oxygens actually, so erase that 2. We need 2 oxygens, so we need a 2 there. That makes 4 hydrogens, so we need a 4 here. And then now we have 4 fluorines, so that gets a 2 there. And then now everything looks balanced. Okay. And then use tabulated data to determine the free energy change for the reaction. Okay, so fluorine gas is in its standard state, so our delta G of formation is 0. Oxygen gas is also in its standard, so that's delta GF is 0. For water, liquid water, what I found is delta GF is minus 228.6 kilojoules per mole. And for HF, I found that delta GF is negative 275.4. So our free energy change for the reaction is the sum of our products minus the sum of our reactants let's put this in a way that's a little bit easier to know what I'm talking about. Delta G of our products minus the delta G's of our reactants. Where each of these need to be multiplied by their appropriate coefficients. So that in this case, for our products, we have 4 times negative 275.4 kilojoules per mole, plus 0 for oxygen. And then on our reactant side, so we have minus, and on our reactant side we have 0 for fluorine, and 2 times minus 228.6 kilojoules per mole for water. If we run this on our calculator here, then we get negative 644.4 kilojoules per mole. Okay. And so the next part of the question says, so there's our free energy for a reaction. Now the next part of the question asks to calculate the enthalpy change using tabulated data. So again, delta HF for F2 is 0. Delta HF for O2 is 0. What I found was delta HF of water is negative 241.8, and delta HF of HF is negative 273.3. And so now we're good. So we can calculate delta H for our reaction, and it's the same steps as for the free energy change. So it's the sum of our delta HFs for our products minus our delta HF for our reactants. And we're going to put in our appropriate coefficients with this. So then looking at our equation again, right, our products are HF and O2, and our reactants are water and fluorine. And we've got a 4 on our HF, so that'll be, just moving this down a bit, so that'll be 4 times minus 273.3 for HF, plus 0 for oxygen, and then minus our reactants. So that's 0 for fluorine gas, and 2 times minus 241.8 for our water. So that's our HF, and that's our water there. And if we work this all through, then we get minus 609.6 kilojoules per mole. Okay, and the last part of the question asks, determine how much heat flows and in what direction when we have a mass of fluorine gas of 34.5 grams. Okay, so to answer this, we need to solve for the moles of fluorine that this corresponds to. So we need our molar mass. So our molar mass of fluorine is 2 times 18.998403 grams per mole, which is equal to 37.996806. And so our moles of fluorine are just equal to our mass over our molar mass. So 34.5 grams over 37.996806, which is 0.90797 moles. Okay, so there's our number of moles of fluorine. And then we can use our delta H to compute our heat flow, as delta H is equal to our heat. But one thing we need to consider is what a delta H of minus 609.6 kilojoules per mole means in this case, or what we mean by a mole. So the way I like to think about this, even though this isn't a proper unit, is mole of reaction. So this is per mole of reaction, or this is per run through our equation. So a mole of reaction is kind of one path through the reaction. So there's 2 2 moles of fluorine per mole of the reaction, 2 moles of water per mole of the reaction, 4 moles of HF per mole of the reaction, and 1 mole of oxygen per mole of the reaction. Okay, so that's kind of the way I like to think about it, because that's really what the mole is that we solve for in our delta H here. So to get our total heat flow, it would actually be Q over N. To get our total heat flow here, it'll be delta H times N, which is minus 609.6 kilojoules per mole of our reaction times, and so this is the moles of fluorine, so we need to multiply this by our conversion here, right? So there's per mole of reaction, there's 2 moles of fluorine, and then we're multiplying by the number of moles of fluorine that we just solved for. And so these would all cancel. And again, mole reaction and mole fluorine are not real units, but I'm just tagging that stuff there just as placeholders so we can keep track of everything. And so running through these factors on our calculator, we would get minus 276.75 kilojoules. And that's also what direction. So minus means that it's leaving, so it's on the product side. So the heat flows, flows toward products, or it leaves the system. Okay. All right. So running through all of our solution here, right from the top. So there's our balanced equation, which looks good. The delta G's of formation that they found are a little different from mine, but that's okay. It depends what table you use. And so these values might differ depending on who measured them, basically. But that's fine. Everything should come out roughly similar, as long as we run through all the equations the same. So 4 times your delta G for HF, and then 2 times that for water. And because of the differences, our values come out a little different, but that's okay. And then for our delta HF, our delta H's of formation are also a little different, of course. Quite different, actually, especially in the water case, but well, the point is, again, that the equation is done properly, and it looks like it is. And so again, our values are going to come out quite different because our delta H's of formation that we had looked up were quite different, but that's okay. Solving for the number of moles, so that looks good. And then To get our heat, we just rearrange this expression. So we multiply our delta H by N, but we need to take into account that there's 2 moles of fluorine per mole of the reaction. And so that's where the division by 2 comes in. And so it's a different value because our tabulated values were different, but everything was done correctly. And so that looks good. And actually, I'm going to stop that here and say that's going to be the end of my session. I hope everyone enjoyed this. If you did, please subscribe to the OneClass channel. If you want to add questions, please follow the links below the video. This has been Jeff Krause for OneClass.